really close. Feel free at any point to remind me that I'm not recording, because that would make me really sad. I do this A so that you know, oh my gosh, I missed something, but I can absolutely go check the video and see what it was that she said. And so that as we're learning maybe how to write out notes on our own without just snapping photos of a board, we have a backup so we're not scared. All right, we're going to start today with relative. That's where we're going to start. We're going to do that. We're going to do some whiteboard problems. And then we're going to talk about graphs. Good news is the graphs hasn't changed, but I'm going to add 2 words, derivative and integral, to your vocabulary today. All right, before we actually talk about relative motion, there's one other thing that kind of gets lumped in with this. It's kind of the same thing. When we talk about reference frames, we have to always define our reference frame before we start a problem. So we have to define, must. Before we start something, so we know what we're talking about. And what I mean by this is, if the situation is, right, I'm standing next to a train station, and I'm watching a train go by, and there's somebody on the train, and overhead there happens to be an airplane flying above, okay? And at the center of all of this, on the train, is a Diet Coke can, right, on a table. The answer to the question, what speed is that Diet Coke can going, changes depending on who you are talking to. If you're talking to me, the observer at the train station, then I'm going to say that that Diet Coke can is moving at whatever speed the train's going. If you're talking about somebody sitting on the train drinking that Diet Coke, it's sitting directly in front of them, they're going to say it's not moving. And if you ask the guy in the plane, flying the opposite direction on top of the train, he's going to say with his X-ray vision that the Diet Coke can is going a different speed, velocity. So it's really important. We have to define what our reference frame is. And that's really where we get relative motion. What is the speed of the Diet Coke can relative to the plane? Relative to me, the observer, standing there. Relative to you on the train. Okay? That's the idea behind a reference frame. The second part of reference frames, that's the part we're going to deal with today. That's relative motion. We're going to talk about that a lot more in just a second. The second part of reference frames is this idea that we don't really talk about very much, but we do have to know in AP Physics C, which is the difference between an inertial reference frame and a non-inertial reference frame. Okay? This is different. This is us realizing that we have been taught high school physics at the Newtonian level. Newton's laws rule. We agree gravity isn't a force, or is a force. It isn't a force. But we agree for high school physics purposes, it is a force, yay. But reality is where physics is today, in the modern physics that we know, we understand that there's Einstein's theory of relativity, gravity isn't actually a force, and there's all sorts of other things called special relativity that are going on. So in AP Physics C, we have to understand that those 2 things exist. And so the main portion we care about is that there are inertial reference frames and non-inertial reference frames. Inertial reference frames are not scary. It just means you're moving at constant velocity. That's the definition. So inertial reference frame means you're moving at constant velocity. That velocity can be 0. That's a constant one. If I'm not moving, I'm moving at constant velocity of 0. In an inertial reference frame, all of Newton's laws work. That's why we care. Okay? That's why in AP Physics C, we need to know the difference. If we say we're in an inertial reference frame, all of Newton's laws are verifiable. They don't just work. I can test them, and I will get the correct answers. That's really important. A non-inertial reference frame means I'm accelerating. Somehow, some way. And now, Newton's laws are broken. No good. Here's a really great example. If I'm driving my car, not my car, I'll be my brother driving in his car. Because in his car, anytime I've ever gotten in it, there's a load of cans, used Dr. Pepper cans, sitting in his floorboard because he's a gross boy. Great. So there's used Diet Coke cans, Dr. Pepper cans, anything he could find on his floorboard at all times. Now, when he's driving along at constant velocity, he's in an inertial frame of reference. So he looks at those cans and they're not moving, which makes sense because nothing is applying a force to them. So based on Newton's laws, there should be no movement or no acceleration. All good. However, when he slams on the brakes in his car, he is now accelerating. He has negative acceleration based on his direction of travel. And now Newton's laws go out the door. He's now in a non-inertial reference frame. What happens to those cans, right? If he slams on the brakes, the cans fly forward, right? That's what happens. They fly forward. And it makes no sense because there's nothing pushing on the cans, so why did they go forward? Well, the answer is because we're no longer in an inertial frame of reference. He's now in a non-inertial frame of reference, and Newton's laws don't work. So that's the idea. That's all we need to know about it. That's it. Conceptually, that's it. On your equation sheet, it says that you're assuming an inertial reference frame for all questions. Good to know. However, are you in an inertial frame of reference right now? Right now. What do you think? Hands up for yes. Inertial frame of reference. Right now, we're in an inertial frame of reference. Hands up for no. What if I told you you're both right? Best we could actually measure in this classroom, we're absolutely in an inertial frame of reference. You guys aren't moving, so we're moving at constant velocity. Perfect. However, we are actually on an Earth that's rotating. If I'm changing directions by rotating, that means I'm accelerating, because any change in direction is acceleration. So I am, and you are, experiencing acceleration right now. Some centripetal acceleration moving you around the planet. So on some very, very, very small scale, we are in a non-inertial reference frame. But that acceleration is so small compared to gravity that we don't notice it. So it's fine. So the answer is yes and no. What we experience, we are in an inertial reference frame, awesome. Technically, we are accelerating. We're all moving around the universe at a very fast speed, so no, we're technically not. But that's an issue for the CERN, not for our measurements in our class. Questions, thoughts, or concerns? All right, that's an inertial reference frame. Let's talk about relative motion. If an object experiences multiple velocities, its total velocity is the sum. This is one of two things we have to learn with relative motion. This is our airplane example. I'm going to do two examples, but this is the airplane example, right? The airplane was experiencing its own velocity. It had an engine, congratulations, it was motoring along in the air, awesome. So it was experiencing its velocity and the wind's velocity. So we added those together, easy. If I'm the kayaker in the river, right, I told that story, I was experiencing my velocity and the river's velocity. And my issue was that my velocity might have been 1 mile per hour and the river was a negative 1 mile per hour, and that's why I had such a hard time. It wasn't very pleasant. Okay, but these are the examples we're talking about. If an object has two speeds. If I'm standing on an airplane and it's flying at 500 miles per hour, let's give you our first example. On an airplane, flying at 500, it's an average. Some of them do better than that, some of them worse. I throw an apple. I don't know where I got this apple. I don't typically bring snacks on an airplane unless the flight's over like 4 hours. But I have an apple, and I throw an apple towards the front of the plane. At 5 miles per hour. It's a bad shot. I'm not really chucking it, just sad. What is the speed of the apple? The actual ground speed of the apple. What do we think? Yeah. 505, absolutely. The correct answer is 505. All I had to do was add the plane speed plus the apple speed, and I get 505. What if I change one word? I am on this plane and I now throw my apple towards the back of the plank. What's the correct answer now? 495. 495. So that's an easy example. 495. Questions about that? Cool. All right. Next example is this. I have a boat. I don't actually have a boat, but let's say I did. I have a boat, and I am operating a ferry service. That's what I do. I operate a ferry service, and I sail my boat across this lake. I mean river. Sorry, it's a river, not a lake. I own a boat, and I offer a ferry service across this river. That's what I do every day for my job, right? My goal is to get people from this side of the river to the other. And this river has a current of 3 meters per second to the north. What direction should I point my boat if it can go, I have a slow boat, 5 meters per second. Oh, that's it. So what direction should I point my boat if my boat can go about 5 meters per second? Turn it on, max engine, I'm going 5 meters per second. So my goal is to go straight across the river. To do that, I need to figure out what direction I should actually move my boat in. If you're like, oh my gosh, this actually isn't a real world example, there's nobody who owns a ferry service across a river, you're wrong. I've done this twice in my life by accident, had no idea what. I was in Australia, driving on the road, and all of a sudden the road ended, there was no bridge. It's like, I don't know what to do. There's one guy on a ferry. It's probably 100 yards across. He just dropped cars off on that side, dropped them over off on this side, free service. There's a island in Belize that was cut in half by a hurricane. It's a really powerful hurricane that came through Belize, and it flooded the whole island and actually destroyed part of it. And so there's a huge river, basically tidal river, going through the two sides of this very small island. You could walk the whole thing in an hour. And there was a guy paid $2 Belizean to take me across and back in his old boat. So this is real. I've experienced multiple times. So if I were to set this up, I know I'm going to be adding together the velocity of me and my boat plus the velocity of the river, and that's going to give me my total velocity on my dinghy, right? The boat's going to experience its velocity and the river's. I add those together and get the total. Questions about this? All right, what is the direction I want to go? Which way do I want to go? To the right or east, whichever one. So that means in unit vector form, my total velocity, I'm going to have a velocity to the right. How much velocity should I have in the J direction? Up or north or down or south? How much? 0. I should have 0J. I want 0J. I don't know what my speed across the river is. I don't know how fast I'm going to go. That's okay. But I know I need to go directly to the right. Nothing up and down. Questions about how I wrote this? So then I have my boat. My boat's going to go at 5 meters per second. That's its speed. In the x direction, it's going to be cosine. In the y direction, it's going to be sine. And then I have the river, which is 3J. Positive. I almost put negative. It's not negative, it's going north or up based on my picture here. So I've written out this statement. The total velocity of my boat needs to be just going to the right. Nothing up or down. My actual boat, I'm going to point in some direction, so it's going to be at some angle, and I'm going to be going my boat's speed, cosine that angle, and then my boat's speed, sine that angle. And then I have the river. Any questions how I set this whole thing up? All right, just like for everything else, I can only solve in one dimension at a time. So, dealer's choice, should I solve the i's, which look like this, or should I solve the equation using the j's, guy, and we don't know this one. So that's two variables. I don't want to solve for two variables. I can't. So I need an equation that only has one. So what that would look like is 0 is equal to 5 sine theta plus 3. So I'm doing the inverse sine of 3 over 5. I'm not putting the negative in my calculator. I told you guys this last time in the unit vector notes. I don't put negatives in my calculator. It doesn't really do me much good, because I'm going to figure out the actual direction by drawing a picture. 36.9. Which direction should that be pointing? I need to go east, and then I need to counter the river going south, so I'm going somewhere that way. So 36.9 south of east. That's the direction I'm going to point my boat. The direction I'm going to point my boat. Questions about this one? Okay. So it's the same idea. If there's ever two things helping the velocity of some object, oftentimes this will be boat and water, plane and air. It could be, there's an example on the whiteboard, a person on a moving sidewalk at the airport, right? Or a person on a train throwing something. Those are basically the objects that we're talking about. If that's what we're doing, then we simply add them up. Okay? Last thing, we'll do two examples of this as well. If I want to find, I'm going to stick with red black. If I want to find the velocity of something relative to something else. So this is the velocity of an airplane with respect to the ground. The velocity of the airplane with respect to another airplane flying a different direction. The velocity of one thing with respect to or relative to another thing. Then I just have to subtract the velocity of whatever it's relative to. So if it's a plane relative to another plane, I'm going to subtract the other plane's velocity. That's what I do. That's how I do this. When I want to find the velocity of something relative to something else, I take the original velocity and I subtract it to whatever it's relative to. This is why when I say ground speed, I'm talking about the true speed of the airplane. That's like what the engines put out. Because if I'm saying relative to the ground, then it's the speed of the plane minus the speed of the ground. Well, the ground's 0. So that would give me the true speed of the plane. The airspeed of the plane would have to be relative to the wind, and I'd have to know what the wind was blowing, right? So that's different. That's why a ground speed or a shore speed would be the real speed of the vehicle, whatever it is, versus an air speed or a water speed or something like that. So let's do this. Have you ever been driving around here, because we live near an airport, and you're just watching the airplanes, and like sometimes they look like they're going really fast, but sometimes it just looks like when they're coming up for a landing or taking off, they're just sitting there. They're not going anywhere at all. They're just kind of sitting there, and you're like, how is that possible? Why do they look like they're not moving? Here's why. Here's my example. I'm driving south on 121 at a crisp 80 miles per hour. A crisp 80 miles per hour. Slightly above the speed limit, that's okay. And I'm watching, and AA, because it always is, trip 7, Boeing 777, coming into land, to the south. They come in around 120, roughly. They can land fast in that, but you can tell when they accidentally land too fast. You're like, ooh, that was not pleasant. Go all the way forward. Versus sometimes they just kind of float in and basically land going 0. So this is an average. So I'm going to do this. I want to know what the speed of the plane is relative to me. So what is the speed of the plane relative to me in the car? That's my question. So I'm going to do this exact math. The speed of the plane relative to me in the car. We're both going south, so the speed of the plane relative to the car would be equal to, the plane goes first, it's going south of negative 120. Me in the car going negative 80, going to the south. And so that means the velocity of the plane relative to the car is only 40 miles per hour. And that's why they look like maybe they're not going anywhere. It's a lot of times also headwind, so they're not even going, like that's the actual speed that they laid out ground speed wise, but when they're floating down ahead of you, if there's a decent crosswind, which if you would believe it, at DFW we regularly hit 40 mile per hour gusts, and they land all the time. So you can definitely see them seem to be floating ahead. Questions about this? Okay, all right, those are my examples. That's reference frames. So